integration or integrals as the area under the curve. In a previous video, we talked about Riemann sums, which were rectangles designed to approximate the area under the curve. So recall that when we said area, it's not a physical area, but a signed area, meaning an integral area can be negative or can be positive, whereas a physical area is always positive. And then when we say under the curve, what we really mean is between the curve and the x-axis. So with Riemann sums, just a quick reminder, and I'm going to do a subinterval here, or some subintervals, and I'm going to do a left-hand Riemann sum, meaning I'm going to draw my rectangle on the left side. That is, I'll get the height using the left side of the interval of my rectangle, and I'll draw a few representative of these Riemann sums. And that the area from, say, A to B was approximated by the sum of these rectangles, whose height was f of x and whose base or width was delta x. How could we find the exact area beneath the curve and the x-axis on the interval A to B? Well, we can shrink the width of our rectangles down to 0. That is, we'll find the limit as delta x goes to 0. And then we can sum together many, many rectangles, really an infinite number of infinitesimally small rectangles. And this will give us the exact area. This notation is a bit hard to use, so we changed it to the following. We use the integral sign, which looks like a stretched out x, of f of x dx, but it's the same thing. It is a sum of what? Of areas of rectangles with height f, or the function value, and whose width is not x, but delta x. Let's investigate this idea of integral as an area a little bit further. And I'm going to draw not a complicated picture, but a more complicated version of f of x than what we've been doing in the previous videos. And I'll add a little bit more detail as we go along. So let's call this function f of x. And I'll put some x values a, b, c, and d like that. I'm going to ask some questions about some integrals going on, but let's make sure we understand some of the notation here. So if I do the integral from a to b of f of x dx, I am saying this is x equals a, and really I'm starting here, and then I'm going to end at x equals b. So we call these our limits. The lower limit is x equals a, is where you start, and then we end at, or we go to, our upper limit, x equals b. I'm going to do a few integrals like this, change some of the limits. And the only question I want to answer is, are the areas, really, are these different integrals, are they positive or negative in value? So I'm not necessarily going to find what they actually equal, But I want to answer the question, do they have a positive or negative value? And let's start with the integral from x equals a to x equals b of f of x dx. Even though we should be drawing really small rectangles, infinitesimally small rectangles, I'll draw a few that are a little bit bigger so we can see what's going on. Recall that the integral is finding the areas of all these rectangles added together. Each integral is made of two parts. A function value times not an x value, but a change in x value. So on the interval a to b, all the function values are greater than 0. They're positive. And since we're starting at x equals a and going to x equals b, my change in x is positive. So I have a positive times a positive, which of course gives me a value greater than 0 or positive. Now what if I wanted to find the integral from b to c of f of x dx? Starting at x equals b, going to x equals c. Again, I'll draw a few representative rectangles. You may notice if you're watching, I'm doing left Riemann sums. Now, what are the values of these pieces? Well, the function values are less than 0. They're negative. But I'm going from b to c, so my delta x's are positive. So I'm multiplying a negative value by a positive value, which gives me a negative value. What if instead we wanted to go from b to a of f of x dx? Always remember, we're multiplying two things together, function value times delta x. That's one small rectangle, and the integral says let's add all of them together. Well, on the interval a to b, we already know that our y, our function values, are greater than 0. But in this case, we're going from x equals a to from x equals b to x equals a. We're going backwards. So in this case, my delta x is negative. So we have a positive times a negative, which gives us a negative. Likewise, if we were to do the integral from c to b, starting at c and going backwards to b, the integral of f of x dx, my function values are negative, my delta x values are negative, which means that that integral would be positive. I have a question for you. Let me draw my function f on the interval a to b. Actually, let me do a to c, and I'll put a b value somewhere in between like that. Is the following statement true or false? Really, the following equation here. Is the integral from a to b of f of x dx plus the integral from b to c of f of x dx equal to the integral from a to c of f of x dx? What do you think? If I consider this in terms of area, my first integral says, let's do the integral from a to b. In this case, positive times positive gives me positive. The second integral is the area from b to c. Does that equal the area from a to c? So does part plus part equal whole? And the answer is yes. What if I do the following, though? What if I leave my statement alone, my equation, but I change the position of B and C? Is this still a correct statement? Let's break it down. The integral from A to B is now everything. It's all of this area. The integral from B to C is an area, but it's going backwards, isn't it? So the value of this one would be the negative of it going forward. So it's almost as if I could subtract this area out. If I do that, does it give me what I want? So is everything, this first part, minus the part from B to C, does that give me the area from A to C? And the answer is yes. This is always a true statement, regardless of where A, B, and C are. It doesn't even matter if the function f is below the axis or not. Let's do one numeric example, but with a few problems. And I'll give you some information about some integrals. Let's say that the integral from -4 to -2 of f of x dx equals -6. And then the integral from -2 to 1 of f of x dx equals 7. And then the integral from 1 to 3 of f of x dx equals -5. Before I ask the questions, let's draw a picture and see if we can give us some information that'll help us solve the problem later on. Now, we don't have to have the exact picture. We just need a picture that kind of tells us what's going on. So, I'll get my x values in here. And it says the integral from -4 to -2 of f is -6. So I'll pretend, just for the sake of argument, that the graph looks like this. And I'm going to put a 6 there. Now 6 is going to be my physical area. Physical areas are always positive. So if the physical area is 6, and I'm going from x equals -4 to x equals -2, would that give me an integral value of -6? And it does. From -2 to 1, I have a positive value, so just for the sake of simplicity, I'll pretend that f is above the x-axis, and that physical area is going to be 7. And the integral from 1 to 3 of my function is -5, so I'll pretend that the function is beneath the x-axis, like that. And I'll put a physical positive value of 5. Now, if this area actually equals 5, recall that physical areas are always positive. If the physical area of this piece is 5, does the integral equal -5? And the answer is yes, because I have negative y's times positive delta of x's gives me a -5. So here's some questions. What is the integral from -4 to 1 of f of x dx? What do you think that equals? Well, it's this first piece, but notice this first piece is negative, plus the second piece, which is positive, so I get a value of 1. How about the integral from 3 to 1 of f of x dx? What does that equal? Well, I'm going from 3 to 1. I know I have a value that is the magnitude is 5. Is this a positive 5 or a -5? Remember that we have two pieces. We have a y and a delta x. The y, all the y's are negative, but we're going backwards from x equals 3 to x equals 1. So your delta x's are also negative. So negative times negative gives us positive. What if we did the integral from 3 to negative 2 of f of x dx? What does that equal? We already saw that the integral from 3 to 1 was positive 5. But I could add to this the integral from 1 to negative 2 of f of x dx as well. So we saw this first piece is 5. How about the next piece, the integral from 1 to negative 2? Don't forget you have two pieces. I already know that its magnitude is 7 from 1 to negative 2 up here. But I have to multiply y values times delta x. The y values are positive, but the delta x's are negative, which means that the integral value of from 1 to negative 2 is a negative 7. So the value I want, the integral from 3 to negative 2, is negative 2. What if I did the following? Let's do the integral from negative 2 to 1 of 4 times f of x minus 3 dx. How could we handle this? Just like with derivatives, where we add or subtract functions, we can just take the derivative of each piece separately and add and subtract them. Since our integrals are antiderivatives, we'll talk about them in more detail in the next video. But since the integral is an antiderivative, if we add or subtract pieces, we can just split them up into separate integrals. And we certainly saw that when we were doing some of the numeric stuff above. But the point is, I could rewrite my integrals if I wanted to, maybe it helps, maybe it doesn't, of 4 times f of x minus 3, or 4 f of x dx minus 3 dx, both on the interval negative 2 to 1. Now what does this equal? Let's look at this first integral only. Just like with derivatives, we have a constant rule. We can ignore the constant and just bring that outside of our summation, which gives the first piece, the integral from negative 2 to 1 of f of x dx with a 4 multiplied on the outside, minus our second integral, 3 dx. I'll rewrite it for us. What does the first integral equal? Well, the integral from negative 2 to 1, from here to here, we know is 7. But we have a 4 out front, so it's 4 times 7. Now, how do we handle this back piece, the integral from negative 2 to 1 of 3 dx? I'm going to pretend like we don't know how to find antiderivatives, and I'm going to do it with areas. I'm going to draw my axes. There's the x and y axis. And I'm going to draw the line y equals 3, because that's my function right here, f of x equals 3, on the interval negative 2 to 1. And we know that the integral is an area, so how can I find the area of that piece? Simply, it's a rectangle whose height is 3 and whose base is coincidentally 3. So we get that the value of this back integral is 9, and the total original integral is 19.